Hello everyone, this is Sarvesh, lecturer in civil engineering, Government Polytechnic, Station Company. The course is reinforced concrete structures. And today I'm going to discuss in lecture 4 the design of TV by limit state method as per IS 456 2000. Objectives. On completion of this lecture, you will be able to know what is meant by T-beams, where it can be used, and what are the advantages of T-beam, and where we can design as a T-beam, and what are the different component parts of T-beams, and what are the different codal provisions for determining the effective width of flange. And we will discuss what is meant by effective width of flange and how to determine for different conditions. And similarly, we will discuss about the maximum and minimum reinforcement required in design of T-beams. So these are the things you will able to know after the completion of this lecture. Before going to start today's lecture, so just rewind what we were discussed in last classes. So till now, we have discussed about what is meant by limit state method and what are the different provisions of limit state method, how to consider the loads and everything. And later we were designed about the singly reinforced beam as well as doubly reinforced. And in last class we were discussed about the design of slabs as per IS 456 2000. And in slabs, it is classified into two types. That is one-way slab and two-way slab. And based upon their longer span to shorter span ratio, it can be divided into two-way slab or one-way slab. Again, in one two-way slab, it is further classified into two types based upon the end condition. That is restrained slabs and unrestrained slabs. And we were solved all the example problems for all the cases. Last class we were solved an example problem on restrained slabs. That means restrained means if the edges of the slab is restricted from the uplift, then we can call it as a restrained slabs, right? So in last class we have designed one example problem for designing the restrained slabs. That means we have calculated the effective depth of the slab and calculated the overall depth of the slab. Then we have calculated the span, effective span, and different types of loads on the slab. And after application of partial safety factor, we were calculated the factored loads, and based on the factored loads we have determined the maximum bending moment and shear forces. And it is a two-way slab, so based upon the support conditions, and it is a restraint slab, we have to use the table number 26 to get the moment coefficient factor. And we have calculated the bending moments based on support conditions. We got 4 bending moments, that is positive bending moments and negative bending moments in both the directions. That means longer span direction as well as shorter span direction. And based upon that, we have calculated the reinforcement for different strips. That means into a slab. you need to divide into three strips. That means middle strip and edge strips in both longer span direction as well as shorter span direction. So we have calculated the reinforcement for all the strips based upon the bending moment and IS 456 IS 456 2000 codal term. So after providing the reinforcement, then we have checked for deflection. That means we have calculated the uh, allowable deflection based upon the L effective by D ratio as per codal provision for simply supported cantilever. There are different conditions out there. So they based upon that we have calculated the allowable L effective by D ratio and we have applied the modification factor. Then we have calculated the actual L effective by D ratio and we got actual L effective by D ratio is less than the allowable L effective by D ratio. There is okay. Then we have checked for shear also. After that, we have prepared the reinforcement details. And before one more thing I missed it, that is torsion reinforcement because here it is a restraint slab. Right? Restraint slab means you need to provide the torsion reinforcement. Torsion reinforcement is provided where the support is discontinuous, right? If the slab is discontinuous, where the slab is discontinuous at that portion, you need to provide the torsion reinforcement in terms of a mesh. So, and what is the provisions of torsion reinforcement and how to provide all these things we were discussed in our last class, right? So, right, this is what we were discussed in our last class. Today, I'm going to start the new topic that is uh, design of T-beams by limit state method as per IS 456 2000. We all know that there are different types of beams. So that means in our first lecture, we were discussed what are the different types of beams. That is based upon the provision of reinforcement. The beams are classified into two types. That is singly reinforced beam or doubly reinforced. That means singly reinforced beam means the reinforcement is provided in only tension zone, right? Doubly reinforced beam means the reinforcement is provided on tension zone as well as compression zone. Why we need to provide reinforcement in compression zone? Because due to the practical issues and due to the restriction of dimensions, so if the load is if the bending moment developed within the beam is very high as compared to singly reinforced beam, and if the dimensions are restricted due to the architecture point of view or any other execution point of view, then we can provide the reinforcement in tension zone to improve the moment of resistance of the member, right? So that is why you need to provide the reinforcement in compression zone. So if you provide the reinforcement in compression zone, then the moment carrying capacity of that member will be increases, right? And you so here the type of beams based on the shape of the member. So if it is a rectangular shape, then we call it as a rectangular beam. If you provide T shape, T shape means so if you provide like this, then we call it as a this is a T shape. So that we call a T beam. L beam means so this is a L beam. So these are the different type based upon the shape. So we'll discuss rectangular. I think we have already discussed it. This is already completed. So these two we will discuss in this design of figure. So it is a little bit different than rectangular beam because it is a rectangular. So these are the T beams because here the depth is the width of the beam is not constant. That is only the difference, right? So we'll see how to design this type of beams. Uh, Before that, uh, why we are going to design a TP or LP? What are the advantages? Because see, while designing in uh, reinforced, singly reinforced first unit, what we assumed that this is a rectangular beam, right? And this is your neutral axis, that is depth of neutral axis. And if you observe the stress diagram as per the uh, IS 456 2000, approximately it will be the straight portion and straight portion, then it will join as a parabola, right? So this is your tension force, this is your compression force, right? So, but what are the assumptions of limit state method in design of rectangular beams or whatever the beams? The the main assumption in limit state method is if you read in your core book, it is clearly mentioned that in tension zone, the total tension force taken by the concrete, right? That means this is a tension zone. Whatever the load is there, that tension force developed with the tension zone is taken by the steel itself. That means we are uh, not transferring the tension force to concrete in tension zone, right? So in compression zone, obviously whatever the load which is developed within the compression zone is taken by the concrete itself. But in tension zone, we are assuming that the total tension force is taken by the steel only, right? So due to this, that means the concrete part in tension zone is approximately zero. It is not contributing any tension force in tension zone. So that is why instead of providing this one, so I can just cut this section because it is no use. So to for economical purpose, just I would like to uh, cut the section like this. So it will become as a key section, right? So suppose so that means you can save all these materials. So whatever the material is there in this portion and in this portion, we can save this material, right? See, design is nothing but what? First thing is design means first criteria is safe. Whatever we are designing, that should be safe throughout its lifespan. And the second criteria is it should be economical. It doesn't mean that if you want to keep the member safe, you cannot provide more number of steel or more number of core sizes. So that is also a bad design. It's a failure. Failure due to the uneconomical, right? So two things you need to remember while designing. One thing is safety. First is safety, and next important is economical. So whatever you are designing, that should be economical, right? So in T beams, if you remove this one, then this total material is safe, right? So if you consider as a T beam, so this will act as a plan. This act as a bed, right? Why we are going this way? Because we are constructing the members as a homogeneous, and this type of beams, L beam, T beam, and L beam is possible to design where you are constructing the slab and beam monolithically. You cannot provide everywhere as a T beam. No, you cannot provide it. So while constructing the slabs, if you are constructing the slab and beams at the same time or simultaneously, monolithical construction. At that place, you can design slabless beam as a T-beam or L. So we'll discuss where we can provide and how to design it. So the main advantage is it can save the materials, right? And we are providing the you can decrease the thickness of the member, that is the width of the member, thickness of the member, right? So we'll discuss it. So that is the main advantage of T beams and rectangular. So that is the concept of T-beams. So generally, as I told now, just now, so same concept because the most of the RC structures, slabs and beams are cast monolithical. Monolithical means we will construct at a time, right? So what we will do is we will make a formwork for slab and beam at a time and reinforcement, and we will pour the concrete at a time. That means it is a monolithic construction, right? So due to that, beams from part of floor system together with the slab. As usual, if you observe any structures, you just see top of the floor. You can see uh, uh, below the slab beams. You can observe the beams, right? So formwork are erected for the beams and the slabs together, and concrete is poured in one operation from bottom of the beam to the top of the slab. This is very important. If you observe any construction work, so first you have to provide the formwork, right? So that formwork is to be done for slabs and beams at a time, right? Then stirrups and bent up bars are extended into the slab. You can observe. Generally, in practical, we will do like that only because the beam size included. So stirrups and bent up bars are extended into the slab. So this results in an integral connection between the slab and beam. So if you are providing like this, that means you are extending the stirrups and bent up bars into the slab. Because why we are extending? Because we are constructing in monolithical construction. That means there should be a good bond between the slab and beam. So if you are providing this bent up bars and the stirrups at the slab, then the result here it will act as an integral connection between the slab and beams. That means it will act as a single member. It cannot act as a separate beam and slab. It will act as a single member, right? So due to which certain portion of the slab acts together with the beam in resisting longitudinal compression in mid-span regions of the beam. This is very important. Due to which, that means if you are providing beam, if you are extending the stirrups as well as bent up bars into the slab, then it will act as a monolithical member. And due to which certain portion of the slab act together with the beam in resisting longitudinal compression in mid-span regions of the beam. So it acts like a flange of the beam. That means, so suppose if this is a slab, and if you construct the beams like this, I'm sorry, if this is a slab, and if you are providing some beams in between, because the lumbar span, you need to provide some beams like. So it is a middle one, right? So this will considered as the span region of the beam. It acts like a flange of the beam. So longitudinal one. So this portion and this portion for this beam. So this portion, some portion will transfer, some portion of load will transfer to this beam, right? So this total, if I consider as, if I cut this one, so this will act as a T beam. If you see, I will show this diagram for your understanding. Okay. So it acts like a flange of the beam. So that means when the slab occurs on both sides of the beam, the section looks like a T section and the beam is known as T beam. Just now I told you, no? So if it is a slab and it is extended to a beam, and for this beam, the slab is extended on both sides of the beam. So this is an intermediate beam, let us say. So the slab is extended on this side and this side. So in this case, it will act as a T section. So see, that is what is in the slab. Of course, on both sides of the beam, the section looks like a T section, and the beam is known as T beam. So this can be designed as a T beam, right? See, from this figure, it is clearly understood that if you consider it totally slab, so this is a 3D diagram, you can easily observe it. So for this beam, the slab is extended on this side and this side. Both the sides is extended. Therefore, if you consider, if you cut the section and if you see the cross section, see, this is beam, and this can be this portion, that means some part of the slab on this side and some part of slab this side is considered as a T section. So that generally we consider half of this span and half of this span, right? So if it is L1, half of L1 by 2, and this is half of L2 by 2 will act. This one will act as a flange of the beam, right? And similarly, this is an intermediate beam, so it looks like a T section. Similarly, if the edge of the beams you can design as a L section, L beam, right? So we'll discuss that one also. We will discuss how to design the L beams. So similar to T beam only, a small difference, right? So this is how you can select as a T beams, right? And this is called as BW. That means width of the uh, web. This will call in T section. Generally, this will call, suppose this is a T section, the component parts of the T section. This will call it as a flange, and this will call it as a web, right? So BW is nothing but width of the web. EF is nothing but width of the flange, and D is nothing but total depth of the beam, right, including the slab. So these are the dimensions of the uh, T section. This is the width of the flange from here to here, and this is the thickness of the flange, DF, capital DF. This is called as thickness of flange, and this overall, that's including slab thickness from here to here, we call it as capital D, overall depth of the beam. And T is nothing but, the distance from the extreme compression fiber to the center of the tension reinforcement, that is effective depth, and this is the area of steel. And BW is nothing but your width of the flange, right? So these are the components parts of the T section, right? So if you see here, actual width of the T-beam, that means the top width of the T-beam, it is equal to the distance between the middle points of the adjacent spans of the slab. it is denoted as generally PF, PF of the flange. And this can be calculated. Suppose this is a continuous slab cross section, right? So this is the intermediate beam. So the clear span of this slab is x1 plus x2 into x1, and here it is 2 into x2. And generally, while designing, we will consider as the half of the span this side and half of the span this side. Why we are considering this one is because while designing, the load is, suppose this is your continuous slab. If we consider this one, right? So if this slab is continuous on this side and this side, so we are assuming that the 50% of the load in this span, the 50% of load is transferred to this slab, and similarly the 50% of this one is transferred to this one. So this total will act as a single member, right? That we call it as the effective width of the flange. So we will discuss all these things. So for the general purpose, the total width distance, equal distance between the middle points of the adjacent span is generally we consider as half of span plus half of the span. So this total we call it as a P. Therefore, B is equal to what? X1 plus BW plus X. So that will call it as a width of the flange of T section. And what is the effective width of the flange? Effective width means the general load distribution is like. So if you consider the flange, this is the flange, and the load is, this is a stress distribution of load within the flange. Actually, it will distribute like this: a straight portion, here also a straight portion, actual stress distribution, and there parabolic. This is the actual stress distribution in the flange. So, for the purpose of analyzing and simplifying it, I am assuming that it is a rectangular distribution by decreasing the actual width of the flange is B, right? But we are for simplifying, we are idealizing this stress distribution as a rectangular portion by decreasing the length of width of the flange to B to B. That we have to determine separately. These both are not equal, they are different, because see, B is nothing but what we just calculated. Actual width of the flange is nothing but x1 plus x2 plus bw. But here you need to calculate the effective width of the flange. That means due to idealizing this stress block, so what is the width of this one from here to here? So as per IS 456-2000, they provided procedure to determine the effective width of the flange. Right? So I hope it is clear that to idealizing and simplifying that and making my stress distribution block into a rectangular portion by decreasing the actual width of the flange into effective width of the flange. Right? For simplifying. So, effective width of the flange is the compressive stress is maximum at the center of the width of the beam, and it reduces with the distance from well. So, therefore, the minimum at mid-span of the slab. It is minimum at the mid-span of the maximum. Maximum at the center of the width of the beam and minimum at the mid-span of the slab. So this concept makes use to constant compressive stress over entire effective width. So that is what we are achieving by simplifying. Constant compressive stress over entire effective width, and force of compression remains same. It is denoted as PF, that is effective width of the flange. Then how to determine this effective width of the TB? So as per IS 1000, the effective span can be determined by as per class number 23.12 and I guess 456,000. So effective width of plant is smaller of these two values. That is L naught by 6 plus BW plus 6 into DF and BF plus X1 plus X2 plus BW. This is already we were discussed. That means X1 plus X2 plus BW is nothing but just now we have discussed. Suppose this is your TV. Sorry, if it is a right. So suppose this is a continuous tab and suppose this is your TV. Better to show that right. Yeah, coming to here. So this is your continuous cross section. So x1 plus x2 plus bw is the weight, and another one is L0 plus L0 by 6 plus bw plus 6 df. So whichever you will get lesser value, that can be treated as your effective width of the uh, flange, right? So what is L0 and yeah? So for T beams, what is L0 and DF? BW is known, that is width of the beam, and DF, what is capital DF? Capital DF is nothing but thickness of, it is already given in IS code book, that is the thickness of flange. That means suppose if this is your T section, just I am roughly drawing it. This is your T section. Yeah, DF is nothing but this one. The thickness of flange is called DF, right? And what is L naught? The distance between the point of zero movements in the beam. So that is called as L naught. The distance between the points of zero movements. Where the point of zero movements, the if we consider two half of the 2 points continuous, then we need to find out where the movement is zero. So the both sides you need to calculate. So that distance where the this movement is zero for this span as well as this span. So that distance we consider as L naught, right? And similarly, BW is nothing but breadth of the wave. That is, this is BW. Anything else given? BF is nothing but effective width of the plant. So this is for T beam, right? And so for isolated T beams, so whatever is given, it is for what this is for adjacent beams on either side. If the adjacent beams on either side, then you need to calculate the effective width of the flange by this formula. That means lesser of these two. If it is isolated one like this, right? Isolated, there is no support beams on either side. So in this case, the effective width of the flange for T beam can be determined by the least of these two formulas. Right? That is BF equal to L naught by 12 plus BW plus 3 into DF, and DF is equal to X1 plus BW. So the values are same. The L naught is nothing but what? Sorry, this is for this is not for T beam. This is for L beams, because this portion we will consider as a L portion. For L portion, you have to calculate L naught by 12 plus BW plus DF. This is for L beam, not for T beams. This is for L beam, right? For L beams, the width of the effective width of the plant is calculated by this case. For isolated, there is different formula. We'll discuss it. Yeah. For isolated case, for T beams, the formula is for isolated T beam. It is already given in IS 456 2000 as per class number 23.1.2. This is Pf is equal to L naught by again L naught plus L naught by B plus 4. This is total by plus BW. This is for isolated TB, right? For isolated TB, for isolated TB to determine the effective width of the plant, we need to use this form. Vf is equal to L naught by B plus 4 plus BW. And similarly for isolated L beams, for isolated L beams, Vf is calculated equal to 0.5 L naught by L naught by B plus 4 plus 4 L naught by B plus 4, and this is whole bracket close plus BW. So this is the equation to determine the isolated L beams for determining the effective width of the plants, that is 0.5 L naught by B plus 4 plus BW. This is for L beams. And for isolated T beams, L naught by B plus 4 plus BW. That means the isolated L beam is half of the isolated T beam. Right? If you observe the equation, same at this point. So like this, you need to determine the effective width of the flange, right? For T beams and L beams in isolated case and normal case. Right? After this, so what is BF effective width of the flange? As I told, is effective width of the flange. This is width of the web. Actual width of the flange, that is B, and distance, the L naught is the distance between the points of zero moments in the beam. X1, X2 is the half of the clear distance between the two adjacent beams. Right? So then, what is the, so this is the first case. If you are calculated all these things, then you can start your design process. So another one is, so what is the minimum reinforcement and maximum reinforcement in T beams and L beams? So as per IS 456 2000, class number 26.5.1, the minimum reinforcement should not be less than the given by the following. That is, A naught by BW into T equal to 0.85 by F of Y. So here, A naught is the minimum area of tension reinforcement, and BW is the width of the web. D is the effective depth of the beam, including the thickness of slab, and F of Y is the yield strength of steel. So from this equation, you have to determine the minimum AS, A naught, right? So that means you need to provide minimum this much of reinforcement as a tension reinforcement, right? If your required reinforcement is less than the minimum, then you can provide minimum reinforcement. Same how we have done it in beams, right? If your required reinforcement, tension reinforcement is less than the minimum, then you need to provide the minimum reinforcement. Similarly, you need to check for maximum reinforcement in T-beam. So the maximum reinforcement in T-beams is 0.04 into BW into D. So where BW is the width of the web and D is the overall depth of the beam. So calculate the maximum bending moment as per IS 456 2000, and then if the required tension reinforcement is greater than the maximum reinforcement, then you have to redesign your section, because you cannot provide more than the maximum reinforcement in tension zone. So because we have to follow the IS codal provisions, right? So whatever you are deciding, the tension reinforcement should be less than the maximum reinforcement and greater than the minimum reinforcement, right? So the two criteria here you should remember. That means if your required reinforcement is less than the minimum, then provide minimum reinforcement, right? That is one case. Second one is if the required reinforcement, tension reinforcement is greater than the maximum reinforcement, then you need to redesign your section by increasing the depth of the beam, right? If it is less than the maximum reinforcement, then you can provide whatever the reinforcement is came for it for resisting the bending, right? So these two things you need to remember while designing the tension reinforcement in T beams as well as in L beams, right? So next one is what are the advantages of T beam, right? So why we are going to design as a T beam instead of rectangular beams or square, right? So the main advantages are, as the slab is monolithic with the beam, it shares compression force and hence increases the movement of resistance of the beam. As I told that while constructing, we will construct the slab and beam at a time, right? And some stirrups and bent up bars will extend it to the slab. So therefore, it will act as a single member. That means it will act as a monolithic. When you apply the load, the both will react, right? So I would like to take the advantage of the slab also, right? If I take advantage of the slab also, then the moment of resistance of that beam will increases. Therefore, the cost will reduces and material also reduces, right? So why I am taking the advantage of that, because we are constructing as a monolithic and it will act as a single member, right? That is why I am taking the advantages of the slab also. If you are not constructing as a monolithic, then you should not take it as a advantage of the slab, because it will act as a separate, right? If you are constructed like a monolithic, then only you can take it as a advantage of the slab, right? So that is the main. The sum of the compression force will take the slab also. Therefore, it will increase the moment of resistance of the beam. Therefore, the depth required will become less. Suppose, see, if it is a single one, then the total overall bending moment should be taken by the beam only, right? So therefore, the required depth is more to resist that much of bending moment. If I take the advantages of slab because of I'm constructing as a monolithic structure, so therefore the required depth will become less as compared to the isolated beam because the slab will also take some bending moment, right? So that is why the required depth will become a little bit lesser as compared to the isolated. And one more important thing is the maximum deflections will become less in T-beam as compared to isolated beam. Right? This is also a very important criteria because see, while designing, generally the beams will fail due to the stiffness factor, stiffness failure. That means deflection failure. So if we design as a monolith, if we design as a T beams, then the deflections will become reduces as compared to the isolated beams, rectangular beams, right? So these are the some of the advantages of T beams, right? So for this, I would like to conclude this lecture. So in this lecture, we were discussed about what is mean by T beam and what are the where it is used and where it is to be designed as a TV and where it is to be designed as a LP, right? And why we are considering as a TV because we are constructing the uh, slab and beam as a monolithic number. So due to that one, so the slab will also take some compression forces. So if I can consider the uh, slab resistance also, so there are the bending moment will be increases and depth required will become less as compared to the isolated. So that is why I am going to design a TB, right? And this can be generally designed in intermediate beams, right? And later we will discuss about the component force of a beam, that means flange and overall depth of the beam, width of the flange, thickness of the web, width of the web, thickness of the flange. And again we were discussed about what is mean by actual width of the flange and what is mean by effective width of the flange. And we were discussed about how to determine this effective width of the flange as per IS 456 2000 for normal T beams, T beam and L beam. There are different formulas to determine the effective width of the flange. And similarly for isolated T beam and isolated L beams, we are given some formulas to determine the actual, effective width of the flange. So what is effective width of the flange? Because for analyzing purpose, the stress distribution is parabolic and minimum at the edges and maximum at the thickness of the width of the flange. So while taking normalizing, an ideal stress distribution is considered, and by reducing the actual width of the flange. Right. So as per that concept, IS 456 is provided some formulas to determine the effective width of the flange for TB and L. So based upon that, you can calculate the effective width of the flange. So after that, we were discussed about what is meant by maximum reinforcement and minimum reinforcement. That means how much tension reinforcement to be provided in TB. So the maximum reinforcement is 0.04 BW into D, and minimum reinforcement can be calculated from the given formula as per IS 456 2000. And whatever the reinforcement you are providing, that should be greater than the minimum reinforcement and less than the maximum reinforcement. You cannot provide more than the maximum reinforcement. If the required or provided reinforcement or required reinforcement is greater than the maximum reinforcement as per IS 45000, then you need to redesign your member, right? Suppose if the reinforcement is less than the minimum reinforcement, then you can provide minimum reinforcement. This criteria is same as what we were discussing rectangular. So for this, I would like to conclude this lecture. Thank you.